Welcome to The Explainer. So today we're diving into what I like to call the ultimate production engineer mystery. It's that classic scenario that literally strikes fear into the hearts of data professionals everywhere. You walk into work, grab your coffee, and bam, you find out a Spark job has suddenly slowed to an absolute crawl. But here's the real kicker. Absolutely no code has changed. Why on earth does a job slow down when the code hasn't been touched at all? Well, today we're going to systematically break down exactly how to investigate this mystery, find the root cause, and, most importantly, solve it. This is going to be incredibly useful, whether you're actively trying to save your company's data pipeline right now, or you're just looking to absolutely crush your next technical interview. Picture this high-stakes, real-world Spark interview question. The interviewer looks at you and says, "Yesterday, your Spark job completed in 20 minutes. Today, the exact same code took 60 minutes. Why?" Now, a lot of candidates will just immediately jump in and guess, right? They'll say, well, maybe the data's bigger, or maybe the cluster's just acting slow. And sure, those are definitely possible reasons. But interviewers expect you to think like a seasoned production engineer. Guessing simply isn't enough. We need a structured, systematic investigation. We can't just assume, we have to prove it, and then we actually have to fix it. To solve this, we're going to follow a golden rule roadmap. 1. Investigating data characteristics. 2. Analyzing runtime behavior. 3. Checking cluster resources. 4. Execution environment changes. And finally, number 5, winning the interview. All right, let's dive into Section 1, investigating data characteristics. Listen, our very first suspect should always be the data itself. Why? Because Spark's entire workload is entirely dependent on the data it processes. Even if your code is 100% identical to yesterday, the data it feeds on might be completely different today.
Let's look at a classic yesterday versus today baseline. Say yesterday we had 100 gigabytes, 100 million rows, and 100 files. But today, we're looking at 350 gigabytes, 320 million rows, and 50,000 files. Obviously, when the data volume literally triples, your runtime is going to increase. Spark now has to read more files, process more partitions, shuffle more data, and write more output. The solution here is usually pretty straightforward. You either scale your cluster resources to match the new baseline, or you introduce incremental processing, so you aren't forced to process the entire massive historical dataset every single run.
But actually, I want you to look closer at that file count. 50,000 files. This triggers the absolute dreaded small files problem. See, even if the overall data size wasn't massive, jumping from 100 files to 50,000 tiny files forces Spark to create thousands of input tasks. The actual computation part might be lightning fast, but opening thousands of tiny files causes this massive scheduling overhead. Spark spends all its time just setting up the reads rather than, actually doing the work. To solve this one, you really need to compact those files upstream, use optimizations like Delta Lake's auto-optimize, or just apply a coalesce operation right after reading the data to reduce the number of partitions moving forward. So we know data volume and file counts matter, right? But how that data is distributed is just as important. And that brings us to data skew. This is when data is unevenly distributed across partitions, causing a single task to take significantly longer than the rest. Just imagine yesterday, every single partition had a nice, neat 100 megabytes. But today, because of some weird anomaly in the data, one partition suddenly swells to 3 gigabytes while the others stay small. Because of how Spark operates, it actually cannot finish a stage until every single task in that stage is finished. To fix skew, professionals often use a really cool technique called salting. This means adding a random prefix to the skewed key to distribute the data evenly across nodes before you execute a join or aggregation. When you look at a task timeline, this skew is incredibly obvious. Tasks 1 and 2 finish in around 14 or 15 seconds. Beautiful, right? But task 3 takes 9 whole minutes. That one huge overloaded partition is delaying the entire stage. The code is completely unchanged, but that one skewed partition makes your total runtime just absolutely skyrocket. But if you salt that key properly, task 3 gets broken down into smaller, much more manageable chunks that finish in 15 seconds just like the rest, which completely restores your expected performance.
So, wrapping up our first layer of investigation, here is your actionable checklist. For the data layer, your action is to compare the input from today versus yesterday. You're specifically looking for changes in overall size, record counts, massive spikes in the number of files, and, of course, evidence of data skew. Now, if the data is totally identical, well, then we move down the stack.
Which brings us to Section 2, analyzing runtime behavior.
Now, this is where we stop asking, why is my job slow? And we start asking, which specific stage became slow? And we do that by opening up the Spark UI to see exactly where that extra time was spent. Narrowing things down like this often reveals the root cause super quickly. Say yesterday, stage 3 took 2 minutes and had a shuffle read of 15 gigabytes. But today, that exact same stage took 18 minutes with a shuffle read of 90 gigabytes. Suddenly, the reason becomes painfully obvious. Shuffle is literally the most expensive operation in Spark because it physically moves data across the network. More shuffle data means a significantly longer runtime. To solve this, you might need to increase your spark.sql.shuffle.partitions configuration so individual tasks just aren't as overwhelmed. You could also filter your data earlier in the pipeline to reduce the volume being shuffled, or broadcast smaller tables to completely avoid the shuffle entirely. Now, while we're still poking around in the Spark UI, specifically looking at the Executors tab, we really need to talk about garbage collection, or GC. This is the process your executors use to automatically clean up Java memory, which actually pauses actual task processing. And here is the big warning. When executors are spending time performing garbage collection, they physically cannot clean memory and process your data at the same time. So if you look in the UI and you see a GC time of 42%, you've just found a massive problem. For context, a healthy GC time might be somewhere around 4%. A huge jump to 42% indicates severe memory pressure. Your executors are spending almost half their time just frantically trying to sweep up memory instead of actually executing your tasks. I mean, no wonder the job is 3 times slower. To resolve this kind of severe GC pressure, you need to either increase your executor memory, tune the Java GC algorithms, like maybe switching over to G1 GC, or check your actual code for memory leaks, like maybe you're instantiating huge objects inside your user-defined functions. All right, here is our recap checklist for the runtime layer. You're going to open the Spark UI, focus heavily on the stage and task pages, and keep an eye out for specific slow tasks that might indicate skew, massive spikes in shuffle data, and of course, those really high garbage collection times. Moving on to section 3, checking cluster resources. So, if the data is the exact same and the runtime metrics don't show any internal data processing issues like a massive shuffle or GC pauses, we have to move to our third suspect. We really have to ask, did our actual hardware footprint change between yesterday and today? Let's contrast the parallelism for a second. Suppose yesterday you had 20 executors to process 200 tasks. That's about 10 waves of execution. Pretty fast, pretty efficient. But today, you only have 8 executors for those exact same 200 tasks, which results in 25 waves of execution. You are running with vastly reduced parallelism here. It's literally doing the exact same amount of work, but with less than half the workforce, so of course it's going to take much, much longer. But you might be wondering, why would resources just magically disappear? Well, there are actually several hidden reasons. Maybe a few executors crashed, which means Spark has to frantically restart them, retry failed tasks, and recompute lost partitions. Or perhaps dynamic allocation is enabled, and the executors were just allocated way too slowly. To solve that one, you can actually set a higher dynamic allocation minimum executors to ensure you have a strong baseline of workers. Or, hey, maybe you just have a noisy neighbor, like another Spark application suddenly hogging all the cluster resources today. In that case, the fix usually requires you to enforce strict Yarn or Kubernetes resource quotas just to properly isolate your workloads. So here's your cluster investigation checklist. Jump into the Executors tab. Your action here is to verify the executor count, actively look for error messages like lost node or retrying task, and calculate if you're processing a whole lot more waves of tasks just due to reduced parallelism. All right, section 4, execution environment changes. You know, sometimes the ground just shifts right beneath our feet without us even knowing. We really need to see if the underlying execution plan or the physical infrastructure changed on us. A prime suspect here is adaptive query execution, or AQE. Now, this is an incredibly powerful feature. It's basically Spark's ability to dynamically change the execution plan at runtime based on the actual data statistics. It's usually fantastic, but it does mean the execution plan can completely alter how the job runs without a single line of code being updated by you. And here is exactly how AQE can suddenly come back to bite you. Imagine yesterday you were joining against a tiny 5 megabyte dimension table. Spark easily used a lightning-fast broadcast hash join. But today, maybe that lookup table grew to 80 megabytes. Spark, or AQE, realizes it can no longer broadcast it.
So it abandons the fast broadcast and completely switches to a sluggish sort merge join, forcing both massive datasets to be shuffled all across the network. The code didn't change at all, but the execution plan sure did, and performance just plummeted. To fix this, you can try increasing the auto broadcast join threshold configuration to essentially force the broadcast, or you can just provide an explicit broadcast hint in your SQL code to override AQE completely. Finally, we have to look at the physical infrastructure suspects, because sometimes, believe it or not, Spark isn't the problem at all. Maybe a really crucial dataset was cached in memory yesterday, but today, due to memory pressure, that cache was evicted. Or perhaps your cloud storage is randomly throttling you, dropping read speeds from 900 megabytes a second way down to 250. It could even be network congestion or just a slow disk. Reviewing your driver and executor logs will reveal a lot of these hidden infrastructure bottlenecks. If you do see throttling, you might need to stagger your job start times to reduce concurrent reads, or, honestly, just upgrade your cloud storage tiers for higher throughput limits. So here is your final checklist for the environment layer. You're going to want to use df.explain and the Spark UI SQL tab to look for any major plan changes and different join types. Then really dig into those logs to look for latency, throttling, or any warnings about missing caches. And finally, Section 5, winning the interview. We have covered a lot of ground today, right? Everything from data characteristics to execution plans and exactly how to fix them. Now, let's synthesize this entire detective framework into the absolute perfect interview response that proves you think like a true production engineer. When the interviewer asks you why the job is 3 times slower today, you look them right in the eye and you say, I'd compare today's run with yesterday's in a structured way, investigating data characteristics, runtime behavior, cluster resources, and the execution plan to identify the root cause systematically instead of guessing. Boom! You just demonstrated deep practical experience. You didn't just guess the problem, you completely mapped out the investigation. So I'll leave you with this question. The next time your production pipeline throws a massive 3x slowdown alert, which of these 4 layers are you going to check first? And more importantly, do you already know which tuning knobs you'll turn to actually fix it?